So welcome back. Today we are discussing about triangulation, and till now we were discussing plane surveying, and now from this topic we are discussing about geodetic surveying. You know the difference between both. In plane surveying we are considering the surface of earth as plane surface, and the lines and angles are straight lines. Okay, but in geodetic surveying we will be considering spherical angles, spherical lines, etc. Okay, so we are considering the curvature of earth. Okay, so triangulation is such a survey. When we make a map of, suppose we are making a map of a state or a district or a country, even a country, we will need triangulation. Okay, if we are considering a map of this area, and by triangulation name it means that we will be dividing this area into smaller and smaller triangles like this. There will be n number of triangles, and from these triangles we will be calculating each of the areas and will add up all these triangles, and thus we will get the plan and the area of a whole district or a whole state. Okay, that's why the name triangulation. Triangulation is such a process where we use triangles or similar figures, triangulation figures, to calculate area and for surveying measurements. Okay, so there are a number of triangulation figures that we use for triangulation. Okay, first one obviously is triangles. There will be a n type of triangles: equilateral triangle, right triangle, okay, or even chains of triangles. This is called chain of triangle. Okay, if you suppose surveying a straight line or strip like portion, we will be using a chain of triangles. Okay, or these are all triangulation figures. Another type is polygons or quadrilaterals like this. Okay, or hexagons, okay, and like chain of triangles we can also construct chain of hexagons like this. Primarily they will all be divided into triangles, but as in technical terms you can express it as hexagons or quadrilaterals, etc. Okay, so these are all primarily they are all triangles as it is triangulation, but you can technically call them hexagons. Okay, if this are the hexagons, you will be using all these things. This is a chain of hexagons. Okay, so in this manner we will be surveying large areas, very large areas, using many surveying instruments and a big team of surveyors, and we will be surveying this area. Okay, so all these methods, triangulation figures are that we are mentioning in this topic is of a little bit obsolete times. Okay, right now we will be doing remote sensing, photogrammetric survey, aerial survey examples. Okay, or GPS, GIS, etc. But these methods and these terms will be from a little more earlier period. Okay, which will not be used currently, but we need to study this to understand the bigger picture. Okay, I hope you get it. So these are the triangulation figures. Next we are moving on to systems of triangulations. There can be a number of systems of triangulation. Let's go into that. So sticking on the first principle of surveying, working from whole to part, we can classify triangulation system into three: primary triangulation, secondary triangulation, and tertiary triangulation. Accuracy and spread of surveying decreasing from top to bottom. Primary triangulation, very large area is covered and highest degree of precision is secured. As we said earlier, it is working from whole to part. As it is the first step, we will be considering the periphery of the total area, and hence the largest measurements and the accurate measurements will be done in primary triangulation. The baseline measurements will be 5 to 10 kilometers, and the sides of triangles will be 30 to 160 kilometers, the largest of the measurements. Secondary triangulation, smaller triangles than primary triangulations are used. Length of baseline varies from 2 to 5 kilometers compared with the first one, and length of triangle 8 to 70 kilometers only usually. The last one, tertiary triangulation. Within the secondary triangles, points are established in short intervals to furnish horizontal contour for detailed surveys. So, within the secondary triangles, we will be establishing triangles with particular horizontal contour, with horizontal measurements and all. Baseline varies from 1 to 3 kilometers, and length of triangle side 1.5 to 10 kilometers. So, next, selection of stations. So, for each triangles we will be needing 3 stations, triangulation stations. If it is a hexagonal shape, we will be needing 6 stations each. So, how do we select these stations? For selection, we will be needing to need to study existing maps of all the topographical area and the structures, and all the possible arrangements alternatives should be studied to select all the stations. So, these are the main points by selecting stations. First point, the station should be clearly visible from each other. Intervisibility should be there. For this, highest available ground will be selected, obviously. Second point, they should form well conditioned triangles. Third one, they should be easily accessible. The triangulation station should be commanding position so that it should be used full for detailed surveys. They should be so fixed that the length of the site is not too large, not too small. They should be so located that the cost of clearing and cutting and building towers is minimum. Last one, triangulation station should be selected so that the line of sight do not pass over chimneys, towns, factories, etc., which may cause irregular refraction of line of sight. Okay. So, these 7 points are to be noted when you are selecting a station. So, next topic, intervisibility and height of stations. So, we know how to select stations and their qualities, and next we are moving on to how do we communicate with these stations. Obviously, this distance will be much higher between the stations, unlike our leveling stations or chain stations. Okay, if this, you suppose this is station A and this is station B, and there is 25 kilometer of distance. Okay, so as this is triangulation, and we, of course, in 25 kilometers there will be curvature of earth involved. Okay, if suppose a man is standing at A and another man is standing at B, both will not be, definitely cannot see each other. They are not intervisible. Okay, so you have to draw like this. Okay, this is the curvature of earth. Okay, and this is A and this is B. Okay, and this distance is 25 kilometers as our example. It can be any number of kilometers. Okay, so only in this image or drawing sketch we are considering curve of earth. Okay, so by proper means, without any height of stations, there are 2 stations without 0 height, A and B are not intervisible. Okay, but if suppose A is raised by 200 meters and the instrument is placed on 200-meter height, and suppose B, the signal man, is raised by 50 meters. Okay, and the staff or whatever the signal is placed at the top of 50-meter height. Then if you join this line, you will get to see the station B. Then only A and B are intervisible. Okay, so this is our key point, the key concept of the topic, intervisibility and height of stations. Intervisibility and height of stations. Okay, so how do you calculate this point? Okay, and for starters, you will be having a point of tangency. So again we are going back to station A and B. Okay, suppose any distance 25 kilometers. Okay, so we are only focusing on intervisibility now. Can A be seen from B, or B be seen from A? Okay, for that, how much distance is the minimum requirement? Okay, so all the calculation will be based on this minimum requirement. That is, when this eyesight, imaginary line of sight, passes like this, like it touches the center point, approximately center point, like just grazes through the ground. Okay, and this point we name it as C, and C is point of tangency. It is important, point of tangency, and it is the point, C is the point through which this imaginary line of sight is just passing through. If this is the ground, the line of sight, if this is the ground, the line of sight is passing like a tangent. Okay, that's why we are calling it as C, point of tangency. Okay, I hope you got it. Okay, and for measuring all these calculations, we have derived an equation for H. H is the height of station. Okay, and it is given by H is equal to 1 minus 2m d square by 2r. H is equal to 1 minus 2m d square by 2r. Very important equation. Okay, where H is height of station. It can be either A or it can be either B. Okay, and M is coefficient of refraction, as it is a very high kilometers, can be any number of kilometers, 100 kilometers, 200 kilometers. Okay, so all this large distance, refraction will be affecting this line of sight. This line of sight will be definitely affected with refraction. Okay, so we will have to incorporate M into the equation, where M's value is M is equal to 0.07 in land and 0.08 in sea. Okay, if this is land surface, intervening ground is land surface, you can substitute 0.07. If the intervening surface is sea, you can substitute as 0.08. Okay, and where D is, capital D is distance to visible horizon or to C. Okay, so C point is known as point of tangency or visible horizon. Okay, so D is this distance. If you are considering station A, height of station A, D is the distance from station A to C. If you are considering H of station B, then distance will be CB. Okay, so that is capital D. And last one, R, radius of Earth, that is 6367 kilometers approximately. Okay, so H is height of station, this height, M is coefficient of refraction, D is distance to visible horizon, AC or BC, depends on which height we are considering. R is radius of Earth, which is approximately taken, which can be approximately taken as 6367 kilometers. Okay, and on further simplification, we can get the equations as H is equal to 0.0673 D square, or D is equal to root of H divided by 0.0673. Okay, so another point to note, you have to substitute D in kilometers, okay, in order to get H in meters. Okay, so do not forget that you will be substituting D in kilometers. We won't be converting it into kilometers, and we won't be converting it into meters either. Okay, so substitute D in kilometers and H in meters. Okay, same in here, H will be substituted in meters and D will be substituted in kilometers. Same, kilometers and meters. Okay, so for the most purpose, these two equations will be considered only in land. If the intervening ground is land, not sea, you can take this equation or this equation. H is equal to 0.0673 D square. Okay, so most of the calculation we will be considering intervening ground as land, as we will be measuring land most probably. So in short, you can take this equation. If the suppose it is C, you should take this, or for elaborate calculations you should calculate using this equation. Okay, so we'll move on to problems. So to sum up, the height of both instrument and signal above the ground depends on the distance between the stations, that distance between A and B. In the previous example we said. Second one, their relative elevations, the height, we said about that 200 meter and 50 meter, that will entirely depend on the intervisibility. And the last one, the profile of intervening ground. That is, if suppose it is a clear ground between A and B, it is very clear ground, and if suppose it is a sea surface, intervisibility will be so easy. A will be so easy to see B, and the height requirement will be very less. And if suppose there is a mountain or a hilly surface, or suppose there is a lot of trees in the intervening ground, it will be very difficult for the intervisibility and more height will be needed. That is the point. Okay, thank you.